In this video, we'll be focusing on solving exponential equations. Now, before we can solve an exponential equation, we need to actually know what an exponential equation is. And an exponential equation is simply an equation where variables occur in the exponents. So we have three different examples below. Notice here, variable in the exponent. Here, variable in the exponent. Here, two variables in the exponents. So we're going to talk through strategies that we can use in order to help us to solve these types of equations for the missing variable value. So to start, we're going to look at a simple exponential equation. And while this looks difficult to solve to start, what you're hopefully noticing is that both of these have a base of 3. And what we're saying here is 3 to some power is equal to 3 to the power of 8. And what you're hopefully thinking about is the fact that we have 3 raised to some power, and we're saying that these are in fact equal. So 3 to some power equals 3 to the power of 8. Well, in order for these to be equal, the only way that they can be equal is if this chunk right here is equal to 8. If this chunk right here is equal to any other number, it won't be an equation, because the only thing that equals 3 to the power of 8 is 3 to the power of 8. 3 to the power of 8 can't equal 3 to the power of 5 or 3 to the power of 6 or something else. So what we can do if we have the same bases here, so notice that we have the same base. If we have the same base with this equal sign in between, what we can do is we can actually set their exponents equal. So if we have that same base, we're saying 3 to the power of something equals 3 to the power of something, then the only way that this equation will be true is if those two exponents have exactly the same value. So we can set them equal to each other and then solve, just like a normal one variable linear equation. So here we subtract 20 from each side. We have 4x is equal to negative 12. Divide both sides by 4, divide both sides by 4, and we find x is equal to negative 3. So here we find that if we take x is equal to negative 3 and we substitute it in here, we would get 3 to the power of 8 on both sides. So now let's use this same thinking to solve the two examples below. What I first notice in this first example is that both of these have a base of 7. So in order for this equation to be true, if these have the same base, then their two exponents need to have the same value in order for 7 to some power to equal 7 to some power. So I can take my two exponents and set them equal. And then from here, simply use my knowledge of solving equations to solve. And I find that x equals 6 will essentially result in this left-hand side having an exponent that is equal to 20, so that 7 to the power of 20 is equal to 7 to the power of 20. Then if I look at this next side over here, I notice that I have multiple x values, but what I do have in common is they both have the same base. So while I don't know what that exponent is actually equal to, since they have the same base, I know that they have to have the same exponent regardless of what that exponent value is. So I can take both exponents and set them equal. So I have 3x plus 5 is equal to 8x minus 45. So I start by getting all of my x's together on the same side. So I have 5 is equal to 5x minus 45. Now I can add the 45 over, so we have 50 is equal to 5x. Divide both sides by 5, and I find that x is equal to 10. So what I can then do is I could take x equals 10 and plug it back in here. So I find that this exponent is equal to 35, as is this exponent equal to 35. So that x value equals to 10 makes both of these exponents equal 35. So I have 9 to the 35th is equal to 9 to the 35th. So now that we have a basic understanding for how solving exponential equations works, let's take a look at situations that aren't so simple. So here we notice that we have exponential equations because we have variable values up here in our exponents. But what I'm noticing is that our bases this time aren't the same. So we don't have like bases with both 3s or 7s or 9s or whatever it might be. So I look here and I notice that I have a base of 5. And here I have a base of 625. And while they don't have the same base, what I'm noticing is that 5 and 625 actually have a relationship. 625 is actually 5 raised to some power. So what I can do is I can use my knowledge of rewriting and use my powers resource to rewrite 625 in a different way. And if I look at my powers resource, I notice that 625 can be rewritten as 5 to the power of 4. 5 to the power of 4 is 625. So if I do some very purposeful rewriting, what I can do is I can actually rewrite this equation so that it contains two sides with terms with exponents that have the same base. So notice here, because I rewrote this 625, I now have a base of 5 on each side. And as a result, I can now take their exponents and I can set them equal. So I can say, well, 2x plus 6, that has to equal 4. And then from here, subtract 6, I get 2x is equal to negative 2, divide by 2, and I find x is equal to negative 1. And ultimately what that does is if I take negative 1 and I plug it back in here, I end up with 5 to the power of 4, which is in fact 625. So now if we take a look at the right-hand side, we notice that this one is even a little bit trickier. So here I have 64 and 32. And I start looking at my powers resource and I notice that there's really no way to get them to have a base, both to have a base of 64, both to have a base of 32. So I have to start brainstorming, thinking outside the box. And what I eventually notice is that they have kind of something in common. I notice that 2 to the power of 6 equals 64. And I notice that 2 to the power of 5 is equal to 32. So while I can't rewrite them both to have bases of 64 or 32, I can rewrite both of them to have a base of 2. So sometimes, depending on the problem that you have in front of you, you're going to have to rewrite both bases. So here I'm going to start and I'm going to rewrite 64 to have a base of 2 to the power of 6. Then I'm going to leave that x minus 2 in the power on the outside. And then I have 32 being written as 2 to the power of 5 with that 2x still raised on the outside. So notice that I just took 64 and 32 and rewrote them utilizing parentheses in a different way, both in terms of 2. So now that they both have the same base, I have to think through how on earth I'm going to multiply these two exponents together. And remember, this is like the powers to powers rule. So this is really 2 raised to the power of 6, and then that being multiplied in its entirety by x minus 2. So really I can rewrite this as 2 to the power of 6 times x and 6 times negative 2, which would be 6x minus 12. And then here, 5 times 2x is 2 to the power of 10x. So I've now utilized that powers to powers rule to rewrite this so that they both have bases of 2. And now that we have the exact same base, we can take both exponents and set them equal. And then from here I want to get all of my x values on the same side. So I have negative 12 is equal to 4x, divide both sides by 4, and I find x is equal to negative 3. So let's do a couple more practice problems together before we move on to fractions. So here I notice that I have bases of 4 and 2. And what I know is that I can rewrite 4 to have a base of 2 if I rewrite it as 2 squared. So here I'm going to take 4 and I'm going to rewrite it as 2 squared and then put my extra exponent of x here on the outside. And then here I have 2 to the power of x minus 3. Now I know here is the powers to powers rule. So this really becomes 2 to the power of 2x is equal to 2 and then to the power of x minus 3. So now that I have the exact same base, I can actually set these equal because they have the same base. So here I have 2x is equal to 1x minus 3. Well, if I subtract 1x from each side, I end up with x is equal to a negative 3. And then from here, if I look at the next example here, I notice that I have a base of 8 and a base of 128. And while I would love to write these both in terms of 8, I can't, so I start brainstorming other options. Now, I know that I can rewrite 8 as 2 to the power of 3. So I start brainstorming and thinking if I can rewrite 128 as a power of 2. Now, even though it's not on my powers resource, what I notice is that I have 2 to the power of 6 is equal to 64. So I start to brainstorm and think, okay, what would 2 to the power of 7 be? And if I start multiplying that out, I realize that it is in fact 128. So what I can do is I can take both 8 and 128 and rewrite them in terms of 2. So here I'm going to rewrite this as 2 to the power of 3, all then raised to the power of 4x. And then I rewrite my 128 as 2 to the power of 7, all then raised to the power of x plus 4. So I've just rewritten those bases in terms of 2. Now from here I need to use the powers to powers rule to multiply these out. So here I have 2 to the power of 12x is equal to 2 to the power of, well, 7 times x is 7x, plus 7 times 4 is 28. So now from here, because I have matching bases, I can set their exponents equal. So I have 12x is equal to 7x plus 28. So I subtract 7x, subtract 7x. I have 5x is equal to 28. Divide both sides by 5 and I get x is equal to 28 over 5. So now let's focus on what we do when we have fractions. Now the first thing that I notice is that the number part in this first problem of the base is 3 and 9. And so I start brainstorming, okay, how can I rewrite this in terms of having the same base? Well, I know that 3 squared is equal to 9. So I'm going to leave this first one on the left-hand side completely alone, and I'm going to rewrite this fraction to be 1 over 3 squared. So now I'm close. I have the same base, but the issue is the fact that I have a 3 in the numerator on the left-hand side and a 3 in the denominator on the right-hand side. Now typically I like to always have positive exponents, but in this case, in order for me to actually use that property of, well, if we have the same base, we can set their exponents equal, I actually have to have them both have the same base in the numerator of a fraction. So what we're going to do here is we're actually going to take this term and we're going to move it up into the numerator. And remember that when this happens, when we move it to the opposite side of the fraction, the sign of the exponent changes. So on the left-hand side, we're left with 3 to the power of x minus 4. And on the right-hand side, because we're moving this 3 squared up into the numerator, we actually get 3 to the power of negative 2. And while I don't typically like negative exponents, in this particular case, it's nice because now we have a 3 as a common base in the numerator, and because of that we can set our two exponents to be equal. So here I now have x minus 4 is equal to negative 2. I can add 4 to each side and find that the x value that makes this equation true is x is equal to 2. Now if I look at the next example over here, I notice that I have a base of 49 and a base of 343. And while I can't write them both in terms of 49, I can write them both in terms of 7, because 7 squared is 49, and 7 to the third power is 343. So here I write the 49 as 7 squared, then to the power of x minus 4. And this one becomes 1 over 7 cubed to the power of x plus 2. So I now have a common base, but one of them is in the numerator of a fraction and one of them is in the denominator. So what I'm going to do is I'm going to rewrite this one with the fraction and move the 7/3 up into the numerator. So here I have 7 squared to the power of x minus 4 on the left. And here I now have 7 to the power of negative 3 raised to the power of x plus 2. Then from here I can utilize the powers to powers, so this really becomes 7 to the power of 2x minus 8 is equal to 7 to the power of negative 3x plus a negative 6, or minus 6, however you like to think about it. Remember that you have to multiply both terms by that exponent attached to the 7. Then from here, because we have common bases, we can set our two exponents to be equal. So we have 2x minus 8 is equal to a negative 3x plus a negative 6. I add 3x, add 3x. So I get 5x minus 8 is equal to negative 6. I add 8 to each side. So I end up with 5x is equal to 2 divided by 5. And I ultimately find that x is equal to 2/5.